So today we're going to do balance a binary search tree, the medium question, and let's get started. So given a binary search tree, return a balanced binary search tree with the same node values. Okay. A binary search tree that is balanced is considered balanced if and only if the depth of the two subtrees of every single node never differs by more than one. Okay. So let's look at the example to kind of understand what it means to be balanced. In this case, we have a node. The depth of its child on the right is 3. The depth of its child on the right is 0. So that differs by 3 and therefore is not balanced. It's also not balanced at this node because the depth is 2 and the depth on the left is 0. So the difference is 2. This node, however, is balanced because its right child is 1 and its left child is 0. So the difference there is only 1. If there's more than one answer, return any of them. Cool. I hope that makes sense in terms of what is considered balanced and what is considered imbalanced. So two things to consider here in terms of an approach is one, we know properties of binary search tree, right? And two, let's try to use recursion. So the properties of a binary search tree are the root will always be greater than its left child, greater than all the values in its left child, and the root will be smaller than all the values in the right child. So what we can take from that is that if we want to get a balanced subtree, we need to find the median element to be the root. And to find a median element, we need to have the values of the binary search tree in a sorted fashion in an array. So that's what we're going to try to do first. Then, once we have the sorted values of the binary search tree, the original one, right, or I guess the values sorted will be the same regardless of the order, then we can basically keep picking the median and then recursing on the left half of the values and the right half of the values and keep picking the median until we've gone down all the way and built our tree. And we'll see how that looks in a second. So first things first, we have to use a wrapper function. So I'll say, okay, values equals self.collect all values, and we'll give it the root, and we'll give it an empty array of the values. And then we're going to return self.rebalance these values. Okay, so now we have this function helper method collect all values we want to define. So define collect all values self root values. So if there's not root, return the values you have so far. Otherwise, values equals self.collect all values. We're doing an in-order traversal because that's how we get a sorted array of the values of a binary search tree. So root.left and then values, values.add append root.val, and then values equals self.collect all values root.right and the current values so far, and then return our total values. So what this is doing is an in-order traversal, basically. Go all the way left, keep going left on left children until you can't anymore, then pop back up 1, check that, add that value to the list, and then go right. Once you've gone right once, try to go left as much as you can, and then once you can't, pop back up, add that value, go right. Keep doing that until you've traversed the entire binary search tree. And once you've done that, once this completes, we'll have an array of sorted node values in this values variable. And now we have to rebalance these values. So what we can do is say, okay, define rebalance takes an array of sorted values, and we'll say, okay, if there's no values, return none. If there are values, we want to get the median. So the midpoint will be length of values divided by 2. We'll say our root will equal tree node, and it takes a value, so tree node of values at the midpoint, right? And then root.left, this is where it gets tricky. So we want to call this recursively on the remaining values, but not just any values. We want the values that are less than the values in the root, because That's the property of a binary search tree. So root.left equal to self.rebalance. And now instead of giving all the values, we want to give the values up until the midpoint, which is where our root is. So all the values that are less than our midpoint. And because it's a binary search tree, we know there are not going to be repeat values. So root.right equal to self.rebalance of values from the midpoint plus 1, since we just already added the midpoint. So all the values to the right of the midpoint in the sorted array. Do that again. And then at the end of it, once all the recursive stack has popped back up, we'll have defined a full subtree to the left, a full subtree to the right, and we're going to return the root, which is our top level node. And this ensures that we have no subtrees, no depths that differ by more than 1, because we're doing this in a balanced way. Whereas we're doing like, okay, take half, take half, take half, take half, take half, take half. So at most there'll be a difference of 1 because of the property of dividing by 2 every time. So that should work. Let's see how it actually behaves. Cool. So given this tree, 1, 2, 3, 4, we rebalanced it as a tree that looks with 3 at the top, 2 on the left, 4 on the right, and then 1 underneath the 2. So you can see that the left child has 2 children, or has a child and a grandchild, and the right child has only 1 child. So the difference is only 1. So yeah, that looks like it'll work. So let's submit it. Cool. So it works. Looks good. Yeah, thanks guys. This is how to balance a binary search tree. If you like my videos, great. Please comment, like, and subscribe. Otherwise, I'm just going to keep going. I'll get better over time, and I'll probably speak slower over time as well. So thank you.